Now, when we're looking at the next group of rocks, the carbonates, we don't really look at roundness, sorting, or grain size, at least at this level. There is some times when we do classify them based on the amount of fine particles mixed in with the larger particles, but in general, we don't pay that much attention to roundness or grain size in the carbonates. So the carbonates are ones that are the result of calcium carbonate deposition in the ocean or in sometimes lakes. In this particular class, we're going to focus entirely on the ocean sediments. If you would go on in geology, you will learn others. I do cover them in historical, but not in physical geology. Now, the thing that all carbonates have in common is the mineral that makes them up has the carbonate ion. Typically, the most common mineral we're looking at is calcite, calcium carbonate. There's another mineral called aragonite that is also calcium carbonate, but a different structure from calcite itself. And there's one dolomite, which is a calcium magnesium carbonate. But we're going to focus primarily on the calcite. So one of the tests, if you remember from the mineral lab, is that if we put acid on a limestone or on calcite, then it will react. So if I take this limestone here and I put some acid on it, of course it bubbles quite vigorously because that acid is reacting with the calcite in the rock and liberating carbon dioxide. So that goes from calcium carbonate to water, carbon dioxide, and calcium and chlorine dissolved in the water. So that's how we can identify, say we were trying to figure out the difference between our quartz sandstone and a limestone, we might be able to put acid on it and that would tell us. Now there are some times when perhaps those quartz grains are cemented together with calcite and that will give us some false information. But if we're not certain, we say, well, it kind of looks like a limestone, then we go ahead and put acid on it. If we think it kind of looks like a sandstone, then we don't need to unless we want to know what cement is holding it together. So what sort of sediment forms these limestones? Well, I've got some modern carbonate sediment. In this one, I've got, this is from a little key near Key Largo called Calto Key that I paddled out to. And the sediment around this key is this little island. Has some shells. It has some gastropod shells, little snail shells. It has some bivalve shells, which are like clams and scallops. It has some coral fragments, which may not be in this particular. Oh, here's one. There's a little piece of coral. So, and then the rest of it is just really fine material, really fine mud. Now, this mud is not the same mud that you would run into in a pond here or a mud puddle here on land. This is all calcite. So all of the grains that make this up were created in the ocean. They were not created on land and then washed into the ocean. They were created mostly by creatures in the ocean. So all of this mud could be broken up shells. It could be broken up pieces of different types of algae that also use calcite in their structure. It could be some sponges that use some calcite to hold their structure up. So these are all the result of organisms making that calcite. And if it became a rock, it might look like this. So this is the Key Largo limestone. So it's from the Keys, and it's about 125,000 years old, where this sediment is from July 3rd last year. So modern sediment, ancient sediment. Notice that there are shells in here. If I look around, there's some more shells, lots of fine material. So this rock may well have formed in a very similar place to this one. Fairly shallow water. In this case, I could stand in it. Even if it wasn't very shallow, it could be, it's very low energy. There's not a whole lot of wave action right where it was deposited because of all that fine material is not typical of waves. A very very high energy water, because the fine particles just get picked up by the water and moved out. Here's another sample of the Key Largo limestone. Now this has a gastropod shell here. There's a bivalve there. Some other fossils mixed in here. They're a little harder to see because they're very broken up. Usually in thin section we can see it pretty well because the individual fossils have different structures. Now this one's pretty easy. This is also Key Largo limestone. There's some brain coral on this side and some star coral on the other side. So it's very often that coral, that new coral will grow on top of old coral. Now, because this is just a loose bit, I have to use some careful looking to determine which way is up. And if I look, notice how this branches out like that. So that means that the brain coral, and this is a bit, see how grungy this top is? This is probably the top, and this coral grew on this coral. So it wasn't the star coral first and then the brain coral. We're looking at the bottom of the brain coral and the top of the star coral. So that's also about 125,000 years old. Key Largo limestone as well. And here's some more star coral. I can tell the up direction here because the coral is going to grow towards the light. I've got one coral head here, another one here. So they may or may not have been the same organism, because corals are composed of lots of polyps that are genetically identical. So they are essentially one organism with many parts. Unlike you and I, we have one mouth and one exit for all of the previously eaten food, so one anus. Coral have many mouths and many anuses, I guess. So each individual polyp has a mouth and an anus, so it eats and poops on its own, but the nutrients are spread and connected. There's connective tissue through the entire organism. So it is a colony of a whole bunch of polyps, but it's only one organism. It's a very strange way of thinking of an organism. We don't think of organisms as having many mouths, but one creature. We don't think of an organism being able to grow its size simply by adding bits to it like corals do. They seem very, very simple, but they're actually extremely biologically sophisticated. So those are the more modern limestones. And these are all actually what we would refer to, well, these are actually reef rock, these two, but these other ones that I'm going to talk to you about are fossiliferous limestones because they are composed of a significant amount of fossils. This one is much older. This is on the order, instead of 125,000 years old, this is more like 350 million years old. And this one has some shells in here. Now these shells are not bivalves though. These are a different creature called brachiopods. They have a shell like the bivalves do, but it functions, the organism is completely different than the bivalves. There's another shell there. There's a whole bunch of little pieces of shells. So this is also a fossiliferous limestone. This one has all of these little stems that it looks like these little lines. These are crinoids, or they are related to like sea urchins and sand dollars, as well as sea stars or starfish. But they're called sea lilies in the modern, the common name for them, but they're actually crinoids is their official name, their scientific name. And we can see the ends of the stems here. They look like little donuts. So this is just chock full of crinoids. So this is also a fossiliferous limestone. And this one's a bit more recent. This is on the order of, say, 100 million years old to 60 million years old. And this one also has lots of fossils. It has a whole bunch of gastropods mixed in there, some bivalves. So lots of ocean sediments, or ocean critters that make up these rocks. And because there are a lot of fossils, we call them fossiliferous limestone or fossil-rich limestone. And this is what a fossil-rich sediment, this is from Key Largo, again, different part of Key Largo. And there's some coral fragments, gastropod right there. These little bits are parts of a calcareous algae. And there might be some more little plates in here I'm trying to look for. There's probably a broken one. Another fossil or a calcareous algae. We've got some pieces of bivalves in here. There's a piece of a bivalve. Here's the little bivalve, teeny one. So these are, this sediment is completely composed of skeletal grains of creatures that passed away or died in the ocean. Now some of those very small grains could also be fecal pellets. So one of the things about, funny thing about carbonate beaches, so if you like to go to Cancun or Cozumel, or looking even in the Florida Keys at this sediment, there are creatures who eat algae on the coral rock like this, and they would scrape they have a little beak. They're parrotfish is the type of fish, and they will scrape at this rock at the coral when there's algae growing on it after the coral has died. They will digest the organic matter, and of course this calcite is of no use to them, so they will poop it out as fecal pellets. And so a lot of the sand on carbonate beaches, like at Cancun, like at Cozumel, and in the Florida Keys, are actually a significant amount of parrotfish poop. So that's just a little bit of trivia for you. So fossiliferous limestones are one kind of limestone. Another kind that is not as common as the fossiliferous limestone, but is very important, that's an oolitic limestone. Now I don't have a sample, a rock sample of this here. We didn't have many on campus, but if you can see that, it is composed of a whole bunch of very little round grains. And those little round grains are called ooids. So these form in very warm, shallow seas, so generally less than 10 meters of water. That's about 30 feet or less, sometimes very much less. Sometimes you can walk around on this stuff, it's so shallow. And that it forms only in very warm seas because, I should say, very calcite-rich, calcium-saturated ocean water, typically. There are some that form in the Great Salt Lake, but that's a different story. But these are ocean ones. These are actually from the Bahamas, so the center of every one of these little circular grains is either a skeletal grain of some kind, or some other sort of grain, could be a broken ooid even, and it rolls around in these calcite-rich seas and kind of grows calcite around the grain, kind of like the way a pearl grows. It's not the same material as a pearl, but it grows layer by layer in a concentric band. And I'll have some images in online to see what those look like. But those are ooids, and a limestone composed either entirely or nearly entirely of ooids would be called an oolitic limestone. So instead of a fossiliferous limestone, it'd be oolitic. And these are not formed, as far as we know, are not formed with the help of an organism. So they are completely inorganic. So even though they are a chemical sedimentary rock like the rest of the limestones, this one is an inorganic chemical sedimentary rock, where these are all biogenic. So each one of the grains in here was created by an organism as the result of biological processes, rather than chemical processes that don't have any organisms involved. So those are the limestones. We're going to focus on marine limestone. These are also generally climate sensitive sediments. For example, these sorts of stony corals only form in warm, shallow seas away from continents. They cannot have all of that sand and mud being dumped on top of them. They suffocate as a result. So these also, we wouldn't have entirely calcite because this stuff doesn't accumulate very fast. So if we have a lot of rivers dumping in sediment, it's going to be mixed in with the calcite, and so we would have maybe a mixed amount of siliciclastic sediments like clays, quartz, maybe some feldspar rock fragments, and then also the calcite sediment. So we will not have purely calcite. There is one other type of limestone that's also forms in the ocean, and that is chalk. Now this is not the same kind of chalk that you put on the blackboard, but you see on my finger there, or my thumb, that is every single one of those little white specks, all those grains, are actually teeny tiny fossils. These are the result of mostly plankton. There's a bunch of calcareous plankton, so these are critters that are single-celled creatures that live in the water column, floating around, or sometimes on the sea bottom. Very, very small, but they're, if you were to take a sample of seawater at anywhere from the very surface down to into the order of, say, 2.5 kilometers or 2,500 meters, then there would be little tiny grains in the water column that are these plankton. Of course, if it's very deep, the plankton aren't going to be alive anymore because most of them live up in the surface waters, because some of them are photosynthetic, and of course at 2,500 meters there's no sunlight. So they live up within the photic zone, which is the first 30 to 40 meters of the ocean, that the sunlight penetrates deep enough that photosynthesis is possible. So this is chalk. This is a deep sea sediment. This is actually from England. This is part of the White Cliffs of Dover. So if you ever watched any World War II films, those are the giant white cliffs that the pilots would look for on their flight back from Europe to know that they were safely back in the UK and not at risk of being attacked by German bombers or fighters. And that particular, at one time in the past, those cliffs were at the bottom of the ocean, accumulating this deep sea sediment of these teeny tiny plankton that have microscopic calcite shells. So that is the different types of limestones that I have: fossiliferous, biogenic in origin, oolitic, chemical inorganic in origin, and chalk, which is also biogenic. And that's it for the carbonates.